Hi, everyone. I'm really excited to welcome Dr. Anne Matsuura to PuzzleX, who's the Director of Quantum Applications and Architecture at Intel Labs. Hi, Anne. How are you today?
Doing well, thank you, Bonnie, and thank you for inviting me here to Puzzle X today. It's my pleasure to be here.
It's a pleasure to have you. I'm really excited to learn more about what you're working on at Intel and all things quantum. So, what exactly is quantum architecture? Because that sounds really exciting.
Yes, so just as classical computing systems need to be designed and need design architecture, so do quantum computing systems. And so at Intel, we're working on both the hardware, the software, and the full system architecture for a quantum computing system. I think it's important to be thinking about quantum computing um, as one unit, right? So it doesn't matter if you have the best hardware in the world or the best software in the world. If it doesn't all work well together as a system, you won't have a performant quantum computing system. And so that's my role at Intel.
At PuzzleX, we're particularly interested in physical technologies and hardware. So, in terms of quantum computing, what kind of hardware are you working on at Intel?
Yeah, at Intel, we're working on silicon quantum dot spin qubits. And we've chosen these types of qubits because it really can leverage our silicon expertise and our manufacturing expertise. They look like one electron transistors. So we can use our manufacturing techniques to very easily manufacture these types of qubits. We actually even have a dedicated 300 millimeter wafer line now at the same fab here in Oregon that we where we create our classical computing chips. We also have the line that where we create our silicon quantum dot qubit chips. And so it's easy for us to, at scale, we have a research and development pipeline where we can in create high volume these research test qubit chips and test them at the wafer level scale. So we're really using the infrastructure that we use for our conventional transistors, and that's the reason we chose quantum dot qubits.
That's really exciting. I was just about to ask you whether this mass production is something that is very near in the future, or is this something that's decades away? What's your take on that?
Well, we're using our manufacturing capabilities to develop this research and development pipeline. So quantum computing is still very much a research field. There are some small qubit systems, compute systems today. So this will be a research area for some time, but we are already using our um, at volume manufacturing capabilities to create our research qubit test chips.
Yeah, that makes a lot of sense. In terms of when you're doing these research tests, are you doing them with the view of a particular industry or a particular application or something that you're really excited to be working on in terms of where these quantum computing applications will be viable?
Well, I have a personal answer to that question because my original background is as an experimental physicist working on high temperature superconductors. And one of the issues for high TC superconductors is that they are very complicated electronic materials. And so in order to they are intractable to simulate on classical computing systems. So personally, my hope is that in the future, a large scale quantum computing system will be able to simulate high temperature superconductors so that we may be able to perhaps design room temperature superconductors in the future.
That's really exciting. And I think with this computing technology, we'd be able to simulate all sorts of materials for all sorts of different applications. So I'm really excited about that as well. In terms of silicon quantum dots, uh, for those that don't necessarily know exactly what that is or what that's akin to in the classical world, what did you mean by, I think you said spin quantum dots, what, and the transistor? Could you tell us more about that, especially for those who maybe are not familiar with exactly what a quantum dot itself is?
Yeah, so we have chosen single electron spin quantum dots. And basically, these things really do look very similar to the transistors that we manufacture in volume at Intel. Um, so it's just a different type of qubit. We're making our qubits out of these quantum dots. Um, Basically, a qubit can be made out of anything where you have a two-level quantum system. And this is just the type of qubit that we think we can manufacture at scale. We can also use our silicon expertise for this.
So where do you see the biggest barriers to entry are for implementing quantum computing or the widespread adoption in industry? What kind of part of your research where you think is the bottleneck at the moment?
Well, I think there are research challenges at every level of the computational stack for quantum computing. But I think for the community, probably one of the biggest barriers is quantum error correction. So uh, we really need to be able to implement error correction in our quantum computing systems. And today, it looks like in order to do that, we'll need tens of physical qubits per logical qubit, which will mean that we'll need, order of magnitude more qubits than originally anticipated. So I really do think error correction research is something that we need to is a bottleneck for the community.
So in terms of this being a challenge for the quantum industry at large, do you think error correction is that's something that's very affected by what kind of hardware? So you mentioned silicon quantum dots, and I know that there's some startups and different things they're using, maybe like diamonds or trapped ions and kind of different kind of hardware. What's your kind of take on how all these hardware options might affect this bottleneck and kind of the solution to it?
Well, I think different quantum computing hardware research teams are looking at various ways at this point to mitigate error. That's what we're doing at Intel. We're looking at more noise resilient algorithms that can be used in the meantime before we have full-blown um, fault-tolerant machines, before we have full-blown quantum error correction. And I think that is something that is that most quantum computing research teams are looking at, as are we at Intel.
Thank you for that, Anne. I was just wondering now, actually, what does using a quantum computer look like? I assume it's not the same as booting up my laptop or getting my phone out and having a really simple user interface. What's that looking like right now from your standpoint?
That's a really good question, Bonnie. So for now, writing quantum algorithms means you need to be aware of what kind of single and two qubit operations are available on today's machines. People are starting to try to abstract that away from the user, abstract kind of the need to have some knowledge of qubit operations to use a machine. But that's the state of the art today, is that you do need to know something about the machine. But I do think that programming languages, trying to make this a more user-friendly experience so that you don't really need to know quantum physics in order to use the machine. That is something that I think is very important for the field, and people are starting to work on that. It's a difficult problem.
I think that's a really exciting prospect. I think traditionally, when I thought about the quantum industry, I felt that maybe a lot of people feel as though they're locked out of the industry because they're not in computer science. But to hear that there is a move towards maybe people don't need to know coding necessarily or quantum operations and being able to understand what's happening, I think that's really exciting. From kind of your perspective, how do you think the quantum community can collaborate more in order to fast track the quantum industry? At Puzzle X, we're really focused and committed to bringing people together from all walks of life to see how we can fast track these technologies. Where do you think there's opportunities for partnerships and collaboration?
I actually think the fact that different parts of the community are working on different kinds of qubits actually is helping to, if not fast track, at least accelerate our progress in quantum computing. I love the fact that there are so many different qubit types out there. Who knows which one will be the most successful, and maybe one will be successful for a certain application area and another will be better for a different application area. But I really do think that the fact that we have diversity in the technologies is something that's super important for us to for the future of quantum computing and to try to accelerate the quantum computing research field.
Thank you, Anne. And I think with the multidisciplinary nature of the industry as well, and from your background with physics and also computing, there is more and more people there is a bigger overlap now in the quantum computing industry where people are binding together. So we thank you a lot for joining us. Have you got any final words about quantum computing and maybe what you're most excited about coming up in the near future in your industry?
But one of the things I'm most excited about in working in the quantum computing research field is, as you mentioned, Bonnie, the multidisciplinary nature of the field. The fact that, I'm working with people from many different technical backgrounds. So I learn things every day, new things every day. And so one thing I would like to say to the audience is, this quantum computing is an area that, whether you're a computer engineer who'd like to know a little bit more about physics, or you're a physicist or chemist who's interested in computer engineering, this could be the field for you, right? I think it's a vibrant research community at the moment, and it's just a really fun topic to work on.
Thank you, Anne. Your charisma is being transferred all over the room right now. So thank you so much for joining us at Puzzle X. And yeah, we hope to see you in person next year.
Yes, definitely. So thank you so much for the invitation. And I'm so sorry I couldn't be with you today. And hopefully next year.
Thank you, Anne.